Welcome, everyone. Before we get, I have a couple of demos to show, but before that, does anyone have any questions? No questions? Hearing no questions, I'm just curious if anyone in the audience has worked with the ZAR data format.
Not me.
Oh, you haven't?
No.
So there's been a lot of interest in ZAR. I'm having trouble hooking up with actual people using ZAR, unfortunately. And one of the projects we're thinking about is basically a vol connector that would read and write to the ZAR data format. So this would be kind of interesting, right? So you have the library just with some environment variables. You'd be able to do all the things you do normally, except instead of going to an HDF file, you'd be reading and writing to a ZAR data store. So there's a few little issues because ZAR is based more on the NetCDF model than the HDF5 model. So we might need to do a little bit of tweaking to get everything to work. But I think overall, it'd be kind of interesting. So if anyone is curious about this, please contact me. I'd be happy to talk more about it. All right, so I see a chat. Okay. All right, cool. So let me just segue then into my demos. Let me share my screen. See, okay. Does everyone see some code?
Yes.
Okay, good. All right. First thing I want to show. So firstly, these examples are all checked into the h5pyd project. So this first one is called compound type example. It's a Python notebook, and you can find it in the h5pyd repo under examples notebooks. And this came up because at some late point, I realized there was an h5py method that we didn't support in h5pyd. So I've added that, and then I wanted to demonstrate how this works. So start with, we do our usual thing here. So let's say, let me start with h5py. So I do this typical trick to switch between h5py and h5pyd. So if use h5py is true, which is here, then we'll import h5py. We'll set our file path to just normal file path. If it's false, we'll import h5pyd as h5py, and the file path will be a domain path, reference to a domain inside HSDS. Okay, let's do that. And then we'll create a new file. So from this point onward, everything is equivalent between h5py and h5pyd. We create a file, and now I'm going to create a NumPy data type. And most people, I think, don't use compound types very frequently, but I think they're actually can be very useful in some circumstance. Here, we're going to do something a little bit crazy. I'm going to create a compound type with 260 fields. And lacking creativity, I'm going to call them A0, A1, A2, all the way up to Z7, Z8, Z9. So we have 10 times 26 is 260. And we just go through here and we append to these fields a name and the data type. So I'm going to have everything to be 6-character string. You could have different subfields. That's all fine. And then we finally say the NumPy data type is a set of fields. Okay, so that goes. And now we create a data set. I'm just going to do normal create data set and set the data type to be this compound data type we just created. And now let's just write some stuff into this data set. So what can we do here? I'm going to do something and call this random.choices with the data set names, the field names, and get 10 fields out of our 260. So here, let me clear all those. So we have N9, E2, A0, T2, etc. And now supposing I want to read just those fields from our data set. There's two ways to go about this. One, I could say dataset bracket colon, get all the values for the dataset, and then bracket names. So what this is doing is reading from HDF5 all the dataset values, and then filtering out to just these names. And we do that, and we get pretty much what we expected. Okay. The other way is to call dataset.fields. And this was the method that I was missing before in h5pyd. So dataset.fields names bracket colon bracket. So it's just basically reversing the colon and the names. What's the difference? The difference is that in the second version, here, let me run it. In the second version, we're asking the library to filter out these names and then return all those filtered values from the data set. And you get the same values. The difference is that the former took 12 milliseconds and the latter took 7 milliseconds. So there's a bit of a performance advantage using this construct. Okay, so that's interesting. So let's go back and use h5py to false. And we will restart, I guess. So now we create a HSDS domain. We do create the same NumPy data type. We create the data set. And we write the values. And we get some random fields. So here, I'm always interested to compare the performance of HSDS and the library. So here that took 12 seconds with library, and we took 169 milliseconds with HSDS. And then if we do the other construct, we got the values in 17 milliseconds. So here we actually have again, it's more performant to use dataset.fields, but it's quite a bit more performant compared to the library. So we have 169 versus 17, so almost a 10x improvement. And I think that may relate to the fact that in h5pyd and HSDS, when you're doing this, you have to move all the data from the data set through an HTTP connection to h5pyd. Here, there's less data you're moving, so apparently it's faster. So that's a useful thing to know, especially if you're using h5pyd. Okay. Any questions about this example or compound types or anything in that area? Right. If not, I'll go on to another example. It's again, it's an h5pyd under examples, and it's called swimmer multiprocess. Let me close. So I had a user who was asking me, he would like to have two processes, right? A writer process that writes to a data set and a reader process that reads from the data set. And the question was, how much bandwidth could he get in the setup? So, and I said, I don't know. So I came across, there was an example in the h5py project, and I've modified a bit so that you can read and write arbitrary amounts of data and then print out how fast that data got moved. So let's see how this works. So if I go to here, so in this example, I'm going to create two processes called swimmer reader and swimmer writer. And so these are both running on the same machine, but in principle, you could have these running on two different machines, at least with HSDS. With the library, it's a little bit hard because Swimmer only works with POSIX local disk. You can't have a file that's, say, on an NFS mount and use Swimmer. So that's a bit of a restriction. And HSDS, it doesn't matter because everything is through the HTTP protocol. So anyway, we have a swimmer reader and swimmer writer. We create this event, and it's basically just a signal to the reader that we've created the file in the data set, and you can start reading data. So we start reader, we start the writer, and then this writer.join and reader.join just waits for those processes to finish. And then when we're done, we print out some stats on how long it took, how much data was copied, and what our throughput was in megabytes per second. And the parameters to this, maybe if I go here, I can just run it. If I say .h, the parameters are file name, block size, and loop count. So, and actually there's an extra parameter called compression. So file name is the name of the file. Block size is how many rows you write in each loop, and loop count is number of loops. So going back to the code, if we look at the swimmer writer first, it creates a file, either with h5pyd or h5py. We create a data set optionally with compression. It's just a one-dimensional data set. And we start with 0 shape, and then we add elements as we were writing. So the flow will be the writer extends the data set, writes to that extended reason, and then loops around for the next iteration. So the write loop, we go for loop count and create a new shape, resize the data set, and then write some random values to that data set. And then this if is instance dataset.id.id int is a little construct to say if the dataset ID is integer, that means we're using h5py. And with Swimmer in the library, you need to call dataset.flush to make sure everything is written out to the file and the reader process is okay to read from the file. With HSDS, we don't do this, and it's not really needed because in HSDS, the reader process isn't looking at the file directly, it's talking to the server, and the server will coordinate the actions of the reader and writer itself. Okay, there's one little trick here. We, after all this loop, we add one more row, and that's basically to serve as a signal that that last block is ready to be read. So you'll kind of see how this works when we look at the reader process next. So the reader, same deal. We open the file, and since we're using swimmer, we have this live_var equals latest and swimmer equals strip. And then we get the data set, and we just loop around here. And if so we have this last count of how many rows we saw in the data set last time we looked. And we get the current data set.shape. And if that shape has gotten bigger, we know that there's data to be read. So we read the block before the current block, and then we update this last shape we saw. If the data shape hasn't been extended, we just sleep for 0.1 second. And once we've gone through all the rows, we're done, and we break out of the while true, and we close the file. Okay, so let's see how this all works. If I do just with no arguments, this will run in using h5py, and it writes, I think, 5 rows, so not much, and it took 0.13 seconds. So that wasn't very interesting. If we write a lot more data, we can say, let's write a million bytes at a time and do that for 10 iterations. That is wrong. Sorry. We have to write swimmer and h5. The file name, the block size, and how many loop iterations. So we copied 76 megabytes, and we have a throughput of 330 megabytes per second, which is pretty good. If we increase this to say 40, I think we're pretty much at our maximum throughput. Oh, 550 megabytes per second. Okay. Now let's try this with HSDS. So to trigger the h5pyd, we add HDF5 : this is another way to distinguish a domain path from a POSIX path. And home test user 1, and let's keep that. Okay, so with h5py and these options, we got 550 megabytes per second. And now we'll use HSDS. And we got 118 megabytes per second. So it's like almost 5 times faster using the library. But again, with HSDS, you have some more options. Like you could have processes running different machines, for example. But here's something interesting. If we add an extra parameter to this, we can specify the compression to be used. So let's use gzip. And so in this case, our data set's compressed, and every time the writer writes to the data set, all the updated chunks will need to be compressed before it's stored to disk. And similarly, the reader, when it's reading from the data set, will need to uncompress each chunk it reads. So it'll be slower than we had before the library and not using compression. So we had the library was 500 megabytes per second with no compression, and with compression, it's 84 megabytes per second. Okay, and then now let's do HSDS. So if we before we had, this is no compression, we had 100 megabytes, 107 megabytes per second, and with compression, we have 102 megabytes per second. So in this case, HSDS is actually faster than using the library. So let's just try that one more time. We had 100 megabytes per second with HSDS and compression. And with the library, we had 84, so slightly faster using HSDS.
Does your throughput value include the time cost of doing the compression itself?
Yes,
And the numbers you're running out are random numbers?
yes. They're
So
random, and you say it shouldn't compress very much.
yeah,
But
it won't compress very much, and then you're still paying the same price. So you're paying the price for
um, but
useless compression.
no, actually it will compress. So let's see here how big is this file? Oops, where's my file? If we do let's age lower MP, so that was 65 megabytes. And now if I run this without compression, it's 300 megabytes. And the reason is because my random numbers, let me get to the writer again. When I create this random, I'm saying rand int from 0 to 100. So each value is 0 to 100,
Okay. Yeah.
and it's in a 4-byte integer, right? So
Sure.
all those
Okay.
high order bits are 0, and
Yep.
therefore we can compress. But yeah, good observation. Yeah, so I thought that was interesting, and it seems both with library and HSDS, we can have a quite reasonable streaming capability. It may not be enough to stream our YouTube Call the Doctor session, but I think for many applications, it'll be totally reasonable. All right. Any other questions on that?
So if this is going on to us like something like Amazon Web Services, where you're paying for both storage space and egress,
Hmm.
you have a balance you have to meet between the file size and your throughput, right?
Right, right.
And
Um,
in fact, if a lot of the
mm,
cost is actually landing on the compression side, which is happening, or decompression, which is happening
mhm.
locally, it might actually be more useful to use the compression
Right,
because
right.
you're not paying
Hmm.
US, if I understand how this works.
Yeah, yeah. Yeah, so yeah, I guess once you talk about the cloud, then this whole cost equation comes into the picture. Um, for writing to the cloud, most providers don't charge for putting data to the cloud. They only charge for data coming out of the cloud. Uh, and I think it's something like 4 cents per gigabyte for egress costs. So yeah, it could add up. And so if you are, it would be more efficient in this case, right, to compress the data before writing. If you're outside the cloud, it'd be more efficient to compress the data before writing to HSDS. And actually,
And
there's
when you say efficient, you mean defining that in terms of time or money?
yeah, it cost,
Cost. Okay.
and likely time as well, right?
Mhm.
Because you'd have less data to transmit. Um, then it turns out though that there's a feature in HSDS that supports what's called HTTP compression. And it has nothing to do with how the data is stored in S3. It applies to how each request is compressed. So when you use HTTP compression, the client that's writing to the server, that each HTTP request will be compressed, sent over the wire. Server receives it, and it'll decompress that request and then go on with its normal processing. And that's a config option in HSDS. It's turned off by default because I found that for most cases, it hurt performance. But if you had, something like this, it might be worthwhile to turn on. Right. And then you'd also want to, and if you care about storage costs, and your data is compressible, using the dataset compression as well would be good, because now it wouldn't affect your egress costs, but it would affect your long-term storage costs. All right. Awesome. Okay, so any last questions? All right. Thanks, everyone, for your time, and we'll see you next time on Call the Doctor. Okay.
Thank you.
Okay, bye-bye.